Hi, in the previous video we learned how a customer maximizes his utility by allocating his or her resources into purchases of the two goods. So now let's make an exercise. It's gonna show us how it works. Look, given that utility function of a given customer is quantity of good X times quantity of good Y, customer's budget is 100, price of good X is 5 and price of good Y is 20. What are the levels, what is the level of good, the quantity of good X and quantity of good Y customers should buy in order to maximize his or her utility? Okay, first thing we do, we build budget constraint, right? Customer budget constraint is given by this, so we get that this is 100 equal to 5x plus 20y, and out of that, we will be able to make the substitutions to Lagrange function. And look, Lagrange function, we repeat the same function, so x times y, now plus lambda, and we put 0 here, right? So 100 minus 5x minus 20y. Okay, and then we move to first order condition. Okay, first order condition, we differentiate. First with respect to lambda, we get the repetition of 100 of the budget constraint, right? We equalize it with 0. Okay, then I differentiate with respect to x, so I'm getting y minus 5 lambda equals to 0, and then I differentiate with respect to y, and I'm getting x minus 20 lambda. Okay, and look, the best way to solve it is using system of simultaneous equations. Why? Because as a byproduct, we're going to get the hashing. So look, what I'm going with this, to do with this, is that I'm moving this 100 to the other hand side of the equation, right? And the rest I'm leaving exactly the same in the way it was, right? And I'm putting it into matrix notation. Right, so we're getting that this is 0, negative 5, negative 20, negative 5, negative 20. 0, 1, that was x, of course, 1, 0. Right, here we've got lambda x, y. We've got that this is negative 100, O. Okay, so all we now need to do is to solve this, but of course we only are interested in x and y. For now we don't touch lambda. In the future we will go back to its extremely interesting interpretation. Okay, so first thing we do, we calculate the determinant, but we see the determinant is simply a border Hessian here, right? So, let's do it step by step. 0, negative 5, negative 20, negative 5, negative 20, 0, 1, 1, 0. Okay, how can I simplify this determinant? Well, the way I would do it is to take negative 5 of the first row and negative 5 out of the first column, right? So we're going to get 25 up front and 0, 1, 4, 1, 4, 0, 1, 0, 1, 0. Okay, so how much is this? 0, 4 plus 4, 4 plus 4, 0, 0, 0. So this is 8 times 25, which is 200. 200 is positive So we know we've got one unique solution. We know that it is a maximum. And because now we've dealt with second order condition, right? We calculated the Hessian. We showed that the Hessian is bigger than 0. Okay, now we just need to calculate x and y, right? So we calculate ax, which in our case we replace the second column, right? -5, -20, negative. Remember, we start with x, not with lambda. 0, 0, -20, 1, 0. Okay. Well, what can we take out of this? That's tricky. Well, I would take -100 out of here. Oh, that's a good idea. Right? And then I would take -5 out of here, which would give us 500. Right? And then, look, what do we have? We've got 0, 1, -20. We've got 1. And we've got 4, and we've got 0, 0, 1, 0. Okay. Finally, using Laplace expansion, we can get rid out of this and this, right? And put minus up front. 0, -4 times -4 times -500. Oh my God, it's 2,000. Okay, now, because of that, we are getting that x in equilibrium, which is equal to ax over bordered Hessian, right, is equal to 2,000 over 200, which gives us 10. Okay, and now y. For y, we substitute the third column. Okay, so we get that this is 0, -5, -20, -100, and 0, I'm sorry, -5, 0, 1, -100, 0, 0. Okay, so again, let's take -5 out of here and -100 out of here. We are getting that this is again 500, and we've got now 0, -5, 1, 0, 0. Here we have 1, 4, 0, 1. And of course, again, we can delete this. We get out of this is 1, 500, and so we get that this is equal to 500. I was making sure I didn't make a mistake. So we get that y is equal to 2. So is equal to ay over border Hessian, which is 200 over 20, which gives us 2.5. And look, now we found the level of a quantity of x and y that gives the customer maximum utility. What is this highest utility? Well, we calculate it as a utility of x and y in optimum. So in our case, this is x times y. This is 10 times 2.5. So we have 250 units of utility. Whatever that means, you'll learn more about it from Dr. Nen. Okay, now let me just point out that when we do exercise like this, a good thing to do at the very end is to illustrate your answer with appropriate graph. Okay, how do we do this over here? Okay, look, we have, first we start by making coordinate space. And look, we need to have budget constraint, right? Our budget constraint will probably look something like this, right? Over here we will have b over py. Here we will have b over px. b is 100 over px. It gives us 20. So at most we can buy 20 units of good x. And on the other hand, we can buy only 5 units of good y, right? Budget divided by y. Okay, the next thing, it's nice to point out, what is the slope of this line, right? What is the slope of this line, right? Negative py over px. Negative px over py. Okay, px is 5, this is 20, negative 1 over 4. And look, makes perfect sense. Here we've got 5, here we've got 20, it should be looking like this. Now, finally, we need to add indifference curve. Remember, of course, we clearly see on this picture that they have only one common point. And over here we can put x in equilibrium, which is 10, and y in equilibrium, which is 2.5. Okay, this is it. This is everything for this portion of this course. And thank you. I wish you all good luck during the exam. Take care.